In 1915, two of the greatest physicists alive had a problem they couldn't solve. Albert Einstein and David Hilbert were stuck. General relativity had a hole in it, and neither man could figure out what was leaking. So they asked a mathematician. A woman. In 1915 Germany. You can imagine how well that went over. Her name was Emmynoether. And she didn't just fix their problem. She discovered something so fundamental that every conservation law in physics, every single one, turns out to be a consequence of a single, elegant idea. Symmetry. Not the pretty kind. The mathematical kind. Though, honestly, it's the pretty kind too. So what do physicists mean by symmetry? Forget butterflies and snowflakes. In physics, a symmetry means you can change something, and the physics stays the same. Rotate your experiment 90 degrees. Do the same experiment tomorrow. Do it in London instead of Berlin. If the results don't change, that's a symmetry. And Noether proved something extraordinary about that. Noether's theorem says this. Every continuous symmetry of a physical system corresponds to a conserved quantity. That's it. One sentence. And it holds up the entirety of modern physics. Time symmetry, meaning the laws of physics don't change from day to day, gives you conservation of energy. Spatial symmetry, meaning physics works the same everywhere, gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum. Every conservation law you've ever heard of is a symmetry in disguise. Let's make this concrete. You throw a ball straight up. It slows down, stops, falls back. Energy is conserved. Kinetic becomes potential becomes kinetic again. But why is energy conserved? Because the laws of gravity don't care what time it is. Throw the ball today, throw it tomorrow, same trajectory. That's time translation symmetry. And Noether proved that time symmetry mathematically requires energy conservation. Not suggests it. Requires it. Here's how the mathematics works, in broad strokes. You write down a Lagrangian, L, which is the difference between kinetic and potential energy. The principle of least action says a system follows the path that minimizes the action integral, which is L integrated over time. Now, if the Lagrangian doesn't change when you shift time by a small amount epsilon, Noether's machinery produces a quantity that is constant along the path. For time shift, that quantity is energy. For spatial shift, momentum. For rotation, angular momentum. Same machine, different symmetry, different conserved quantity. Rotational symmetry deserves its own moment. A figure skater pulls in her arms and spins faster. Angular momentum is conserved. But this isn't some separate law bolted onto physics. It's a direct consequence of the fact that the universe doesn't care which direction you face. Rotate your lab by any angle, and the equations of motion look identical. Noether says that must produce a conserved quantity. It does. Angular momentum. The skater doesn't know she's doing abstract algebra. But she is. Now, about Emmynoether herself. She was born in 1882 in Erlangen, Germany. Her father was a mathematician. She wasn't allowed to formally enroll in university, so she audited classes. 4 years. She earned her doctorate in 1907. And then she couldn't get a paid position because she was a woman. When Hilbert tried to get her a faculty position in Göttingen, the philosophy department objected. Hilbert's response was magnificent. I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathing establishment. Physics was, arguably, her side project. Her real legacy is abstract algebra. She essentially founded the modern approach to ring theory and module theory. She proved that every ascending chain of ideals in a ring eventually stabilizes, and rings with that property are now called Noetherian. Half of modern algebra is built on structures she named and theorems she proved. The woman who couldn't get a teaching salary had her name on a third of the textbook. Her theorem gets even deeper in modern physics. Gauge symmetry, the internal symmetry of quantum field theory, produces conserved charges through Noether's theorem. Electric charge conservation comes from a symmetry. Color charge in the strong force comes from a symmetry. The entire standard model of particle physics is built on gauge symmetries that Noether's theorem converts into conserved quantities. Every particle interaction obeys her 1915 result. And then there's the twist. When a symmetry breaks, the conservation law breaks too. The universe cooled after the Big Bang, and certain symmetries shattered. That breaking is why you exist. A perfect symmetry between matter and antimatter was slightly broken, and the tiny surplus of matter left over became every galaxy, star, planet, and person. Symmetry gives you conservation. Broken symmetry gives you existence. Emmynoether died in 1935, at 53, from complications after surgery. Einstein wrote in the New York Times that she was the most significant creative mathematical genius thus far produced since the higher education of women began. Her theorem remains the deepest single result connecting mathematics to physics. One sentence. Symmetry implies conservation. Everything else is a consequence.